Hello and welcome to this recorded e-learning module for designers trying to understand FPGA timing closure. My name is Frank Nelson. I'll be your instructor for this module. This module is about how to gain timing closure. While this topic is very large and encompasses lots of design techniques, software usage, etc., we're going to try to give you a high-level view of how you can get your design to meet your timing needs. Regardless of your experience, this module will help you reduce your learning curve and get productive faster. This module will help you understand how your synthesis tool, the ISE software, your HDL coding style, and other factors can affect your ability to meet your system timing objectives. Now, timing closure is a large topic that encompasses many of the topics we cover in the Essentials of FPGA Design in the Designing for Performance courses, and this module is not intended to replace any of that. In fact, timing closure is such a large and important topic that many of our customers attend our live courses just so they can get a handle on this topic. Now, we recommend that you take the time to attend both of these courses to learn all the critical design considerations you must make when targeting any FPGA device. And as I mentioned before, I've yet to have a customer in my career who doesn't attend these courses every 3 or 4 years and tell me that it isn't worthwhile. The simple fact is these devices and this software changes so much that it's important to keep up to date in this industry. After completing this module, you will be able to describe the overall flow for gaining timing closure, specify the key elements in gaining timing closure, describe the importance of your HDL coding style, explain the importance of using cores in your design to gain speed, and list the most effective implementation options that can help you. Well, this flow diagram is pretty impressive. In fact, it's kind of remarkable that knowing this industry, we've managed to narrow it down to just this kind of scope. So this diagram here is intended to kind of cover all of timing closure and what are all the possible decisions a designer might have to make. It's kind of a high-level view, but again, it's kind of simplified even. Some designers might say, well, you could do this and do this, but we really wanted to try to come to some consensus with a lot of our Xilinx experts. Now, we're going to touch on all of these topics, although briefly in this RAL. Now, this diagram shows you the things you must consider from the very beginning of the design process, and this starts at the very top on the left-hand side at 1. The first thing you have to understand is that what is a reasonable expectation of performance? Now, this is strictly dependent on your chosen device family, and as you know, they're each different, whether that's whatever vendor, whatever speed grade. Each has its own dedicated set of hardware resources, and each has slightly different performance. So the first thing is, are you taking advantage of the dedicated hardware resources? That's usually a factor that most customers are using to decide what product family is right for them. Well, when we talk about performance, we're really talking about how your internal logic will map to the CLB resources, that is, the LUTs and registers. For this sake of discussion, we're not concerned about block RAMs, DSP slices, or dedicated processors or gigabit transceivers. We kind of figure that's a high-end functionality that you're going to choose a device because that device has those resources. But what we're talking about is how you get your generic HDL code, which will end up synthesizing and mapping to LUTs and registers, and then get that design to meet your system timing needs. That's really most often your timing critical path. It's seldom ever in dedicated hardware. To do that, you first have to choose an appropriate device family that can meet your performance needs. And we're going to talk about what kind of performance you can expect from your device and how to determine that. The next topic is planning a good design pinout. This will directly affect your input and output delays, so it's important you follow some good guidelines, and we'll try and talk about a little bit of those when we get up to it. But in general, like you say, you're planning your pinout to be placed for your board level needs, but also trying to place it to meet your internal needs of timing inside the FPGA, so it's going to be placed near your logic. HDL coding is perhaps the most important topic, and as you can see, it comes very early in the design process. This implies that the more effort you put into building a better design will actually help you be successful much sooner rather than later. Next is making appropriate timing constraints for your design. As you may or may not know, the implementation tools use timing constraints to determine if you're happy with the results. So in effect, if you don't write timing constraints, you're telling the tools you don't care about the speed. This means that writing effective timing constraints is pretty much always done by every user, even if their performance expectations are modest. Finally, before synthesizing, it's recommended that you choose a design strategy and goal. This is an automatic way to guide the implementation and your synthesis tool, that is XST, This will enable algorithms and software operations that will help you meet your objectives. So it's a very simple way. Not all of our customers use it. For some customers, it's very high level. They'd rather get in there and customize the options for synthesis and place and route on their own. But it's up to the user. After considering all of these first few steps, most customers would have a pretty good design that is not a waste of time to synthesize and place and route. Although many experienced customers might not wait this long and in fact skip some of these steps. We're guiding you through this process in the most thorough way so that you understand our guidance correctly. The first yellow triangle you see here is guiding you to review your synthesis tool's timing estimates, and hopefully this will give you confidence that you can meet your system timing goals. If you're way off, then we recommend changing your code or at least changing your synthesis tool settings to hopefully generate a more useful netlist that will have a better chance of meeting your timing goals. After that, you implement your design and use the static timing analyzer utility to determine if you actually met your timing goals. Till this point, the only timing information you had was a timing estimate, since completing implementation is required to know your design's routing delays, as well as the final placement. And until that's done, the tools can't tell you this is what your performance will be. Now, this may then require you to make an HDL coding change, make a path-specific constraint, evaluate the placement of your logic, which might require you to change your tool settings, or make a design change, such as replicating a piece of logic to reduce a net delay. But no matter what it is, if the timing analyzer tells you that you did not meet your timing, you will need to make a change. But if you met timing, you're done and can now generate a bit stream for programming and do other things, such as debugging or probing the design with chip scope, whatever. Next, sometimes to change the tool settings, designers will use the Smart Explorer or Explore Ahead utilities. And this is the Explore Ahead is specifically a utility that's included with our Plan Ahead software, but both have similar functionality. And they're basically high-level ways of running the implementation and synthesis process even with different options to see if we can find a combination that will generate faster results than you've already gotten. So it'll basically generate different implementation results. It's worth trying, but the caveat here is that you run the tools multiple times, so you may end up locking your machine for quite a while. So this is why it's further down. Even though it's easy to do, it's further down the list. We don't like to tell customers to go try this and then call us back a few days later and say it didn't work. Now, next, if that still does not help to meet your timing, then users can consider making area constraints with the Plan Ahead software. Plan Ahead makes it easy to evaluate the placement of your logic and find a better place and route solution. We'll talk a little bit about that later on. After that, another implementation can be completed, and if you still have not met your timing, then you can try running the tools differently in whatever manner you choose. But now we're starting to get desperate. Your last option is to migrate to a faster speed grade, larger device, or faster device family. And as you know, that would of course affect your budget, and of course it's very late in the design cycle to be doing that. So sometimes customers get very irritated if they're in that situation. The big issue here is, did you understand the speed capabilities of your device family? Was that initial timing expectation reasonable, or were you overly optimistic? And again, we like to try and cover timing estimation early on so you get an idea. If that's the case, you're going to have to re-architect, re-synthesize for a different device, etc. And this might mean inserting additional pipeline stages or getting another designer to evaluate your HDL code. But the key is you have to find out why you have too many levels of logic in your timing critical path. So as you can see, this is rather methodical and challenging, but the key is that the sooner you evaluate your HDL code and optimize your design to use the FPGA's dedicated hardware resources, the sooner you're going to meet your timing. Well, the first thing you need to understand is what kind of performance your chosen device can get. Now, this can be found by reading a data sheet, and you'll usually find that FPGA manufacturers will provide a maximum clock frequency. The first thing I want to point out, that's peak performance, which means that that's one logic level. That means the data path will go from a register through a LUT to another register, usually the same LUT and register on the same CLB or slice. But the key thing here is to understand that that's optimal. Now, those frequencies are based on some of the shortest routing resources, but they're usually still easy to be accessed. So it's not unusual for a customer to get those used, but the key thing is one LUT. How do you build logic that will get down to one lookup table? Well, we'll talk a little bit about those HDL coding styles and some of those things and some of our other RELs. But the key thing is to understand that that speed is not typical. That's maximum speed. What you need to anticipate is what is typical performance and be able to determine what is typical performance for the chosen device family. And that requires a good timing estimate. Now, after you have built your design, you can get a timing estimate in a couple of ways. You can calculate a manual estimate from your data sheet, which is pretty good, and I'm going to show you a little bit how to do that. You can synthesize a timing estimate, which is also very good, but will require you to code the design. But I'll note here, synthesis tools tend to use a loading model, and that tends to be a little more pessimistic about the routing delay, which is not bad, but still, you need to understand that there's a flaw in the estimate there. A lot of synthesis vendors would say, well, we all do that so we don't get sued or whatever. Well, that's okay. But the key thing is for you to understand that that number usually is a little pessimistic. Next is you can synthesize the design and then run it through the mapper. That's the first phase of the implementation process, and that's usually gotten through very quickly as part of the implementation process. So really all the tools we've done is taken the design and run it through the mapping or grouping of logic, and then you can generate a timing report that will give you a timing estimate as well. And of course that will use an estimated routing as well. Now the key thing to understand is, again, logic delays at this point are known. LUT delays, register delays, clock to output times on registers, all that's tangible. And in fact, you can find that from the data sheet. But your net delays are not known. And that's really why we say when we're using an estimate, we're working with an estimated net delay. Now, synthesis tools, as I mentioned, have access to the logic, but not to the net delays. Until we route the design, we don't know what those nets will be. To resolve this, the tools use a loading model, and as I mentioned, that's pretty uncertain. Experienced FPGA designers know that another estimate is to use what we call the 50-50 rule. Other customers use like the 60-40 rule. That means that your logic delay, in this example of 50-50, would be half your delay, and the routing might be 50% as well. Or if you're using 60-40, usually logic is 60% and routing is 40%. This assumes that your logic delay, which is a TI low, which is a LUT delay, will include a setup time and a clock to output time on a CLB register, will typically equal an average net delay. You get the idea? The logic delay here, the LUT, the setup, and the clock to out will be equivalent to the net delay for an estimate. Now, from a Vertex 6 datasheet, using a -3 speed grade, again, you can just find this in the actual timing delay models. We see here we have our numbers, a LUT delay of 0.18, etc. And this equates to a logic delay of about 0.77 nanoseconds, which means that your route delay should be about the same, for an estimate of 1.5 nanoseconds for one logic level. And this corresponds to about 650 megahertz. And again, that's an estimate. But the key thing to note here, that's one logic level. When you make this model map to two logic levels, that's two LUTs in series, so we go register, LUT, LUT, and then go to another register, it equates to around 3 nanoseconds. 3 logic levels over 4.5 nanoseconds. And this is why it's important to understand that you have to code with minimal logic levels if you expect to achieve peak performance. So to this point, when it comes to actually estimating your timing, you must remember a couple of things. Number one, a logic level is a clock to out in a CLB register plus a LUT delay plus a setup time on a CLB register. And your performance is greatly impacted by the number of logic levels, just like we saw with our sample calculations. It increases as you go to 2, 3, 4, and 5 logic levels. FPGA experts know if you want to improve your system speed, first you must make sure you have evaluated the number of logic levels on your timing critical path. So as we work through performance estimates, the key thing to understand also is that the least experienced customers will typically design the worst case path at 3 to 5 logic levels, usually even 4 to 5 logic levels. But this will depend upon the device architecture. Recall, as you're using Spartan 3 or Vertex 4, you have a 4-input LUT architecture versus Vertex 5, Vertex 6, and Spartan 6, which have a 6-input LUT architecture. So you can start to see that as you move to the newer devices, these wider architectures can decode more logic, which should reduce your overall number of logic levels. So in other words, the design targeting newer devices should run faster, besides just having a smaller integration. But in this case, we're talking here, you get to 5 logic levels, we'd be running at over 7 nanoseconds and almost 129 megahertz in the worst case operation. That's actually rather untypical. I would say that a lot of the newest customers now would be probably at 3 or 4 logic levels. Now, most experienced customers will typically design their worst case path at 2 logic levels, and that should mean that an average customer, particularly one who has experience, should be able to get over 300 megahertz. But this will depend on the effort you put into following your good HDL coding techniques and optimizing your design for the FPGA. This means using the dedicated hardware resources as much as possible, verifying your HDL coding techniques, and of course analyzing the timing with a timing analyzer report, and then from the timing analyzer report trying to decide what is best to do. Replicate logic to reduce a high fan-out net, pipeline to reduce logic levels, use an alternative design technique to reduce logic levels, use your synthesis options, or likewise using advanced implementation options to just improve the place and route solution. But at least this gives you an idea of what you should be able to expect. So as I mentioned, Plan Ahead and the I/O Planner are included with the ISE software. The I/O Planner can be launched from the Project Navigator. On this slide, we see the I/O Planner has been opened and a design has been loaded. Note that no logic is highlighted in the device view, just the I/O pins. That's because the HDL code was yet to be associated or synthesized. However, the pins have been assigned. We can see a number of the pins are color-coded. Other key features include a very elegant cross-probing that allows you to see the group of pins associated with each clock region. In this case, a clock region is selected in the device view, and the associated pins become highlighted as well in the package view. But what you must remember is that you're going to use this to evaluate the routing delays from your source or destination logic to your I/O pins. This slide shows an example of a design that was laid out early. In this case, we have selected a component and are showing all of its pin connections. As you can see, the green lines show the effective, but not the actual routing from a component to its output pins. The component in yellow is a considerably large component using about 20% of the FPGA resources. So the first question is, do you see anything wrong with this pin layout? Yep, it's bad. This is the case because we have prohibitively long routes to and from the chosen I/O pins. It would have been better if the designer had anticipated placing the necessary I/O pins in associated groups rather than spreading them across the die. To fix this, it will take the tools a lot of implementation time and effort, but the better solution would be to move the poorly assigned I/O pins, which may or may not be possible depending where you are in the design flow. The next step after improving your pin layout is to make certain that you have used good HDL coding styles. And to help with this, we provided a number of free recorded learnings on our website on basic HDL coding as well as optimizing your code for Vertex 6 and Spartan 6. In case you're targeting Vertex 5, there's even a Vertex 5 HDL coding techniques REL as well. And what these modules really do is they try to encourage what most successful FPGA designers would expect to do, and that is use synchronous design, build finite state machines, and test their synthesis result for them, and perhaps optimize their encoding. We also discuss instantiation versus inference, hierarchy management, as well as common HDL coding mistakes for FPGAs. When we start getting into the specific architecture coding techniques, now we're talking about managing device resources, specifically muxes, shift register LUT, some of the dedicated functionality that's built into these FPGAs that requires particular HDL coding techniques, including flip-flop configurations, control signal usage, reducing control sets, etc. All of this is very important to optimizing the speed of your design. You should also know that using the dedicated hardware resources is critical to obtaining peak performance. Now the cores we're talking about are optimized components. These are designed by Xilinx experts who have in-depth knowledge about the FPGA architecture, and these components target some of the dedicated hardware resources that are beneficial to building optimum speed. We also talk about, in the core generator module, instantiation of a core and how you can get that instantiation template from the core generator. We talk a little bit about some of the other cores that are available as well. The beautiful thing, though, is they offer guaranteed functionality and this saves time during simulation, as well as increases the design speed because the cores contain mapping and placement information that have a predictable performance that is constant over device size and utilization. Next, you should be using timing constraints, in particular global timing constraints. On the left in this slide, in this example, we see a design that has been implemented just with pin assignments. Note how the logic is effectively grouped by default. In this case, the timing achieved was reasonable. But when we used global timing constraints, that is the period, the offset in, and the offset out timing constraints, we obtained a different layout that has improved the speed by over 20%. And note that the pin assignments were still maintained. Now, timing constraints are going to define your performance objectives. As I mentioned before, if you don't use timing constraints, the tools basically assume you don't care about the timing. Now, you over-constraining your designs, the first thing to keep in mind is, gets you nothing, but it costs extra power time. As we tell people, the key thing is to define timing constraints that are going to define your actual timing objectives. And of course, if they're unrealistic, that means you really didn't do a timing estimate to begin with, and so you really don't know what you're in for. So it's very important that you spend a few minutes and you calculate what you expect to get speed-wise for your design, and that you understand the global timing constraints well enough to make the appropriate global timing constraints to get just that performance. Now note, the global timing constraints REL will provide a great deal more information about the global timing constraints that we're going to cover here. Unrealistic timing constraints, though, will cause the tools to stop, and that's because there's a mechanism as part of the post-map stack timing report information that will stop the tools if it realizes you put unrealistic timing constraints. After implementation, check out the post-place and route stack timing report to determine if your objectives are met, and more importantly, if your constraints failed, use these reports to determine the cause. This is critical. This is really the most important benefit of using the timing analyzer. We cover timing report generation as well as the functionality of the timing analyzer, as well as, more importantly, what you can do to improve your timing based on what the timing report says. We include all of that as part of the Designing for Performance course. Now, timing constraints include the three main global constraints, that is the period, the offset in, and the offset out. The period covers your synchronous to synchronous delay paths, that is delay paths between two flip-flops. The offset in covers input pin to synchronous element delay paths, and the offset out covers synchronous to output pin delay paths. We also support the use of path-specific constraints to describe false paths and multi-cycle paths. Multi-cycle paths, of course, often occur when you have multiple flip-flops that are disabled on alternating clock edges. The use of all these timing constraints is appropriate. Now, we cover the use of global constraints in the Essentials of FPGA Design course, as well as our free recorded e-learning module, and we cover path-specific constraints in the Designing for Performance course. Now, we also wanted to show you an easy way to set your XST synthesis as well as place and route software options. Now, Xilinx provides you with the preset software options that are part of the design goals and strategies. This is an easy way to run both synthesis and implementation without knowing how the software works. Now, this is helpful if someone does not want to understand the various options and when they can improve their timing results. Now, first of all, I want to point out that when you use this function, you have a number of settings that have already been lumped together into preset combinations. So we've taken the combinations and we've optimized them for a balanced setting, which is a default, which means it'll weigh device utilization as well as timing performance in the implementation process as well as synthesis. There's a timing performance setting, which will ignore area or power optimization and go for just speed. Likewise, there are area reductions, minimum runtime or minimum implementation time, as well as power optimization. And all of these strategies are visible to you, and you can edit those strategies within the tool set very easily. Now, this slide is intended to point out the next phase of time enclosure, which is the most powerful synthesis options that are included with all the high-end FPGA design software. Now, as I mentioned, there's many synthesis options that can help you obtain performance and area objectives. There's timing-driven synthesis, finite state machine extraction, retiming, register duplication, hierarchy management, resource sharing, and physical optimization. And we discuss all of these as part of our synthesis options recorded learning, which is also covered in our Designing for Performance class. These are primary options that are available in all the high-end synthesis tools in the FPGA industry, so odds are your tool has all this functionality built in. We also have another REL called XST Synthesis Options, which also discusses some of the other dedicated features that are built into XST to help you optimize your synthesis result. We explain some of the caveats of these features as well as what the powerful functions are intended to do. After synthesis, the implementation tools include several options that can manipulate the place and route solution found. These options are covered as part of the Designing for Performance course, but some of the best functionality includes the overall effort level for both map and par, which will allow the tools to work harder on map and par, the extra effort level, which will sometimes help you get better performance, but sometimes does not, at the expense, again, of a longer implementation time. And then finally, the use of the tools automatically using timing constraints during map, which is called the dash timing option. And this will guide the tools to actually group the logic closer together, even within CLBs if possible, and that will allow for minimum routing delay to be needed. So again, the intention here is to work harder during the map phase as the placement phase, rather than the route phase, because in the end it's much more powerful to use timing constraints and use these options during map and placement to get better timing results than to just reroute the design. Understanding your system performance and locating any timing critical paths is important to deciding how to improve your timing. Now, these timing reports, as I mentioned, are made with a timing analyzer. The function of this tool and the reports it generates are covered as part of the Designing for Performance class. But in this case, we wanted to point out a few things about a simple example. So in this case, we've got a period constraint. You can see at the very top, which is included in your constraint summary. This will show you number of paths analyzed, number of timing errors, and the length of your critical path. But the period constraint, again, covers your synchronous to synchronous element delay paths. So when you look at the path detail below, you'll see that it starts at the very top with a clock to output time in a register, goes through a number of lookup tables, and finally gets set up in the last register. And of course, the beautiful thing about this is placement information, as well as routing delays and logic delays, and the hierarchical representation of each of the elements along the data path are all described. Now, based on how this data path breaks down, as you can see, it's easy to see how many logic levels are included. In this case, there are 4 LUTs in series, 4 TI lows you see in the path below, and that gives you a real quick idea. Too many logic levels might be the problem here. But there's lots of different possible problems, including your net delay, needing logic duplication, etc., that can be part of the problem. But the beautiful thing, of course, is the marvelous detail. And again, this is all for worst case operating conditions for each of your data paths. In this example, we see a simple data path being reported, and in this case, it can almost be taken from the previous slide. We see a clock to output time on top, 3 lookup tables, that's 3 TI lows, and then a setup time on the last flip-flop. And of course, we can see even the fan out on each of the incremental net delays. We see a hierarchical representation of each element along the data path, and we see our total delay. Now, this path was constrained to 3 nanoseconds. But the real thing to ask yourself is, what is the primary cause of the timing failure? And the first thing that I see here is, of course, that the 1.5 routing delay for the net out of the first LUT is a little excessive when you compare it to the other net delays. But, of course, this has got a fan out of 1. So one of the things that might cross my mind right off the top is placement. Where are those LUTs in the registers? Perhaps there is some other logic that's forcing this logic to this data path to be spread out across the die. But of course, you have to go through a little bit of experience of reading these reports to not only understand what they're telling you, but more importantly, to try to understand what you need to do to gain timing closure from them. Another software utility is Smart Explorer within the ISE software. This will iterate through the implementation process, trying different combinations of properties, and then automatically stop when all the timing constraints are met. These options that I'm describing here are those that are going to control the place and route as well as the resynthesis of your design during the implementation process. And they include the overall effort level, the extra effort level, use of global optimization, retiming, register duplication, logic optimization, using the optimization strategy or cover mode, and as well as allowing logic optimization across a hierarchical boundary. So the intention here is it makes it easy for the customer to not have to understand the tools, and yet they can try various options very quickly, but again at the expense of a lengthy runtime. And here we can see the different iterations that could have been attempted. In this example right here, we have actually taken the design and we started to run Smart Explorer, and as you can see from the diagram, there were a number of different settings that were set up under different names like map runtime, map reg dupe, etc. And these are based upon the various options that were set. But the key thing to note here is the tools ran the first set of combination of options, and it met the implementation in just a very short period of time. And that's probably because, again, this design wasn't very big, and it went through implementation pretty quick. But at least you get an idea. You can then see the results, and then you can pick the one you want and copy that result into your project directory, and then that way you can evaluate each of the different results that were made if you would like. But the key thing also to note is the best result is saved into the project directory by default. Similarly, the Plan Ahead software, that's the area constraint tool I mentioned that is included with the ISE software. It includes a similar functionality called Explore Ahead. And again, this will run multiple runs with a wizard and select from numerous synthesis and implementation option settings for each run. Now, by the way, just so you know, these combination of settings are not random. These are tested by our experts, just like within the ISE tools for Smart Explorer, and these have been pre-optimized to see which combination seems to work best. You'll have to specify a directory location to store the results and specify a host also if you want to run on a workstation. And that can also be beneficial to get you better speed. After completion, you can load up each of these results and compare the results. As we work further through the timing closure flow diagram that I described earlier, we have pretty much used all the easy solutions to gaining timing closure. Now, if we need more speed, we'll have to get into making area constraints with Plan Ahead, which is actually not that hard, but the key is having your code fixed. Having tried running synthesis with all the different synthesis options to maybe see if we can get a better result, and have you given the implementation tool options a chance to help you? If the answer is yes, and you've tried all these things, and you still need more speed, then you can consider making area constraints. Now, to learn more about making area constraints, we encourage our customers to attend one of our Plan Ahead software courses. This will teach you all the basics, as well as all the advanced features of Plan Ahead, and also discuss various strategies in which to make good area constraints. You can also listen to the area constraints REL that we have posted. Now, in this example, we're looking at the same design we had before, and as you can see here, we have the logic all highlighted in yellow, and all the green represents the routing to the various I/O pins. But you have to first of all note the logic of the highlighted in yellow and where it's placed on the die. And the first thing you probably note is it's really kind of sprinkled all across the die. Well, that could be good and bad, because if it's the tools pull that logic closer to the source of destination by spreading the logic out, then it makes sense that it's doing that to meet a timing constraint. But likewise, if I force the tools to keep that logic consolidated, then maybe I'm robbing myself of that opportunity. But as we discussed in the Plan Ahead course, there is a method to this, in making good area constraints that will actually make a lot of sense for your design. And this slide shows you an example, again, of using Plan Ahead as part of that design process of making area constraints. And as you can see, as we basically took that same design we saw before, and we've basically done a default grouping or done a hierarchical segmentation of the design into 6 different area constraints. Now note, these are just P blocks, or what we call representations of grouping of logic. So these little regions we see specified here are not indicative of where that logic should be placed on the die, or the relative size, or relative to how much logic is in each area constraint. But the key thing here we're really doing is we're just looking at a hierarchical representation of the design, and we're seeing these red and the one blue line reflect the intercommunication of the logic in each of the area constraints. And what you should probably be looking at and recognizing from this diagram is that the area constraint, or P block number 3, is the most critical. And the reason is because, of course, it talks to all the other various area constraints. Now, likewise, you can see area constraint number 5 has these long green lines, which means, of course, that we're routing the I/O signals to and from the area constraint across the die. So from this, it would make sense if area constraint number 5 was in the upper left-hand corner. But one of the key things to note here is that area constraint number 3 needs to be near the center of the die, and really most importantly, it needs to be touching all the other area constraints, because it, of course, communicates to all of them, which would kind of infer that it should be in the center somewhere. Now, I'm not going to try and torment you by reviewing all the details of timing closure again. So if you're wondering how all the details of the slides I just covered went into this, just replay this recording and note that I took you through this whole diagram and described all the possible solutions to gaining timing closure. Note that I did not describe the last option, which was buying a faster part. Trust me, if you get to this phase, it's not usually fun, but it does happen. And I will just say that we appreciate your business. The tools are not designed to recommend this option, but I will say that if you have an idea how fast your device can operate and good HDL experience, then you should not have to do this. In the end, most customers would say, I made this mistake while I was learning to do my first implementation. In summary, timing closure is a design activity, not an automatic activity, and not a push-button flow. Gaining timing closure requires good design knowledge as well as good HDL skills. Also, good FPGA architecture knowledge is a requirement, required. Significant tool experience is, of course, essential, and proper design planning, especially with pin assignments early on, are very important. Again, my name is Frank Nelson. You've been listening to the Time Enclosure Recorded e-learning module. Thanks for listening.